I'm Ridmi Hesara and welcome back to my channel. In today's video, we are diving into fundamental concept in data structures tree representation. We will understand what trees are, how to represent them using arrays and linked lists, and why they are important, all using a simple real-world analogy. Let's get started. What is a tree in data structure? A tree is a nonlinear data structure made up of nodes. Each node stores some data and connects to other nodes, kind of like a family tree or an organizational chart. In a tree, the topmost node is called the root. Nodes connected to below are children, and nodes with no children are called leaf nodes. The structure flows down from root to leaves, forming a hierarchy. This is what a tree data structure looks like. Each element in the tree is called a node. The topmost node or the starting point of the tree is called the root. A node that has child nodes is called a parent node, and the nodes that descend from another node are known as child nodes. A node with no children is called a leaf node, and a node that has at least one child is called an internal node. The level of a node means its distance from the root, and we always start counting levels from the zero. The degree of a node is the number of direct children it has. And finally, the height of a node is the longest path from that node to any leaf node beneath it. This terminology helps us describe and understand how trees work in a structured and consistent way. Now that we understand the key parts of a tree, let's connect it to something more familiar, a company hierarchy. Let's make it super simple with a real world analogy. Imagine a company. At the top, we have the CEO. That's our root node. Reporting to the CEO are department heads like the engineering manager, sales manager, and HR manager. These are our internal nodes. Each manager has team members reporting to them, like developers or sales representatives. Those are the leaf nodes. Why tree representation matters? Now that we know what trees are, the next big question is, how do we represent trees inside a computer? There are two major ways: array based representation and linked list based representation. Each has pros and cons, and the choice depends on the type of a tree and the operations we want to perform. Array representation concept. In array representation, we treat the tree like a level-wise structure, like a heap. We store each node in an array index and use formulas to find parent-child relationships. Left child of index 2i plus 1, right child of index 2i plus 2, parent index I minus 1 divided by 2. For example, if node A is at index 0, its left child is at index 1, its right child is at index 2, and so on. This method is great for complete binary trees where every level is fully filled. But if the tree is sparse or irregular, it wastes space because some indices will be unused. Let's take a look at the Java code for this. We create an array, insert elements level by level, and use the formulas to navigate. This Java class tree array demonstrates how to represent a binary tree using an array. Each node is placed at a specific index in the array, and the position of each child node is calculated using formulas. Left child of node at index I equals 2i plus 1. Right child of node at index I equals 2i plus 2. This approach works best for complete binary trees. In the beginning of the code, it declares an array of size 10 to hold the tree nodes. Each element of the array represents a node in the binary tree. The tree has a fixed size. Then the add method adds a node to the specific index. It first checks if the index is within bounds. If yes, it stores the value like AB at that index. The display method displays all the null none nodes in the tree. It loops through the array and prints out the index and corresponding value. Then the main method, it creates an object of tree array and populates the tree. So on, A is placed at index 0, it means root, B at index 1, C at index 2, D at index 3, E at index 4, and F at index 5. Each line shows the index in the array and the value is stored there. Next up, linked list representation. In this model, each node is an object with three parts: data, left reference, and right reference. The node literally points to its children. No formulas needed. This makes it very flexible and ideal for dynamic or irregular trees. You can insert or delete nodes easily, and the memory usage is efficient. No wasted slots like in arrays. This is the Java code of tree representation using linked list. What this code does. This program represents a binary tree using a linked list approach, where each node is an object that is stored. Its data, a reference to its left child, and a reference to its right child. This is a flexible and dynamic way to build trees in Java. Let's look code breakdown by step. First, node class. This is the basic building block of a tree. Each node contains data and the actual value, left and the right reference to its left and right children. The constructor sets the node's data and initializes child references as null. Then the class tree-linked. This class holds the tree. It contains one main field which points to the topmost node of the tree. Then the method displayTree. This method prints the tree structure. First, if checks if the tree has a root. If yes, it prints the root node, the left child and the right child. If no root is present, it prints tree is empty. Then the main method. This creates a tree object. Set up three nodes, A as root, B as left child of A, C as the right child of A. Finally, it calls display trees to print the node relationships. So the output of this program is the root node is A, the left child is B, and the right child is C. This is a perfect example of linked representation where each node dynamically points to its children using references. Let's now compare array representation and linked list representation of trees based on some key features. Structure type. In an array, the size is fixed when the tree is created. You need to define the maximum number of nodes in advance. In a linked list, the structure is dynamic. You can add nodes as needed without setting a size beforehand. Then the memory usage. Arrays can waste memory because if some nodes are missing, their index positions remain empty. Linked lists use memory only when a node exists, so they are more efficient for sparse trees. Flexibility. Array-based trees are harder to modify. Inserting or deleting nodes often requires recalculating or shifting indices. Linked lists are more flexible. You can insert or delete nodes by simply changing pointers. Ideal use cases. Arrays are best for complete binary trees like heaps where every level is filled. Linked lists are suitable for all types of trees, especially when the structure is irregular or changes frequently. Then the code complexity. In arrays, you need to manually calculate child and parent indices using formulas. In linked list, each node directly points to its children, which makes the code simpler and easier to manage. If your tree is complete and will not change, go with array representation. And if your tree is dynamic or uneven, linked list representation is the better choice. Thanks for watching. If you found this video helpful, give it like and subscribe for more DSA tutorials. If you got any questions, drop them in the comments. I will happy to reply. Until then, keep coding and keep learning. Bye bye.